The foundational functionality that this entire system depends on is the ability to identify when the user requires assistance through monitoring the barbell's kinematics. One of the ways we can achieve this is to utilize computer vision. By setting up a camera to the side of the squat rack, we can add a colored sticker to the barbell, which will let us track its movement, similar to how it's tracking the object on screen. We can plot the vertical movement over time, as well as the assistance levels output U, which range from 0 to 1, representing none to full assistance. An algorithm will continuously be ran to monitor the position and velocity of the bar over time. If the bar falls below a certain threshold for a given amount of time, it will identify a failure and ramp up assistance as needed until the bar reaches back up to home position. We will use the output U to control our actuator.
From the electrical standpoint, this diagram shows both the physical architecture of our spotter system and its Simulink model at the top. The microcontroller sends up, down, stop, and speed reference digital commands, which are conditioned through a relay module and a digital to analog converter to safely interface with the VFD. The VFD then drives the induction motor using three-phase AC to create the lifting and lowering motion of the hoist. Finally, we track torque and speed to verify that the system responds correctly under the barbell load.
For the alternative approach, this is the hardware that is modeled in the Simulink model here. The step input represents the Arduino's command that feeds into the H block, which drives the DC motor, in this case a linear actuator. So when I run this for the on case where we're supplying 1 volts, we will see that the motor speed starts from 0 and eventually settles to a constant value. And then that speed causes the linear actuator to displace. And you can see that's increasing. I also wanted to show a small scale representation of this implemented. So this is the Arduino, this is the H bridge, this is the battery source, and then this is the motor. So when this person presses the blue button, it will move the motor in the clockwise direction and then counterclockwise for red, which basically shows that the H bridge can be used to control the direction of the motor.
Our proof of concept includes a multitude of modular components to install onto an existing squat rack, which includes our hoist, which acts as an actuator to control the vertical force for our lift, a barbell safety rack in order to rack the barbell after a completed lift, a rail attachment to enclose our hoist wire and also connect other attachments to an existing squat rack, and finally our barbell arm attachment to apply a vertical force onto the physical barbell. And throughout the design of this mechanical device, there was a multitude of risky and technically challenging aspects that we need to cover, primarily around user safety. Specifically, we want to make sure that the components that are not supposed to be touched by the user don't get touched and are enclosed properly. Specifically, we want to make sure that moving components such as our hoist wire is able to lie within our enclosure to make sure to minimize the amount of misuse of the user and also injury.